GPS stands for Global Positioning System, which is a satellite-based navigation system that allows users to determine their precise location anywhere on Earth. The GPS system consists of a network of satellites in orbit around the Earth, ground-based control stations, and GPS receivers. GPS receivers, which are commonly found in smartphones, cars, and other devices, receive signals from multiple satellites and use the information to calculate the receiver's exact location, as well as other data such as speed, direction, and time. The GPS system provides accurate positioning information by measuring the time it takes for signals to travel from the satellites to the receiver. GPS technology has a wide range of applications, including navigation for vehicles and pedestrians, surveying and mapping, outdoor and fitness activities, aviation, maritime navigation, and even tracking of people, vehicles, and assets for various purposes like fleet management and security. It's worth noting that GPS is just one of several global navigation satellite systems, GNSS, in operation today. Other prominent GNSS systems include GLONASS, Russia, Galileo, European Union, Beidou, China, and NavIC, India. These systems work in a similar manner, providing positioning and navigation services to users worldwide. GPS calculates the receiver's exact location using a process called trilateration. Trilateration involves measuring the distance between the receiver and multiple GPS satellites to determine its position. Here's a simplified explanation of how GPS calculates the receiver's location. 1. Satellite signal transmission. The GPS satellites continuously transmit signals that include their precise location and the time the signals were transmitted. 1. Signal reception. The GPS receiver picks up signals from multiple satellites within its range. The receiver measures the time it takes for each signal to travel from the satellite to the receiver. Distance calculation. Using the time it took for the signals to reach the receiver calculates the distance between itself and each satellite. It does this by multiplying the signal's travel time by the speed of light, which gives the distance the signal traveled. Trilateration. Once the distances to at least 4 satellites are known, the receiver uses trilateration to determine its location. Trilateration involves intersecting spheres or circles to find the common intersection point. In the case of GPS, the spheres or circles represent the distances from the receiver to each satellite. By finding the intersection point of these spheres or circles, the receiver can determine its position in 3-dimensional space, latitude, longitude, and altitude. Error correction. The GPS receiver accounts for various sources of error, such as atmospheric interference, clock discrepancies, and signal delays, to improve the accuracy of the calculated position. This is done using techniques like differential GPS, DGPS, which compares the receiver's measurements with known reference points to correct for errors. By repeating this process continuously and considering signals from multiple satellites, the GPS receiver can track its position as it moves, providing real-time location information. GPS signals are generally designed to work best in open sky conditions, where there is a clear line of sight between the GPS receiver and multiple GPS satellites. However, GPS reception can be challenging or even impossible in indoor environments or areas with limited satellite visibility, such as dense urban areas, deep valleys, or heavily forested regions. Here are a few reasons why GPS reception can be problematic indoors or in areas with limited visibility. Signal blockage. GPS signals can be obstructed or weakened by physical barriers such as buildings, walls, roofs, and foliage. These obstacles can block or attenuate the signals, making it difficult for the receiver to acquire and maintain a strong signal lock. Signal reflection and multipath. Indoor environments often have reflective surfaces such as walls, floors, and furniture. When GPS signals bounce off these surfaces before reaching the receiver, it can cause a phenomenon known as multipath interference. Multipath interference can introduce signal distortions and inaccuracies, making it challenging for the receiver to determine its precise location. Weakened signal strength. GPS signals become weaker as they pass through obstacles or travel longer distances. In indoor or obstructed environments, the received GPS signals tend to be significantly attenuated compared to outdoor conditions. This weakened signal strength can make it difficult for the receiver to acquire and maintain a reliable signal lock. Despite these challenges, there are techniques and technologies that can help improve GPS reception in indoor or obstructed environments. Assisted GPS, AGPS. AGPS utilizes additional information from cellular networks or Wi-Fi hotspots to assist in determining the receiver's location. By combining GPS signals with other positioning sources, AGPS can help improve location accuracy and acquisition speed, even in challenging environments. GPS repeaters. GPS repeaters are devices that receive GPS signals from outside and retransmit them indoors. They help extend the GPS signal coverage to areas with limited visibility, allowing GPS receivers to function indoors. Indoor positioning systems, IPS technologies use alternative methods, such as Wi-Fi signals, Bluetooth beacons, or magnetic fields, to determine indoor positions. These systems can provide location information in environments where GPS signals are not available or reliable. Sensor fusion. By combining GPS data with other sensors like accelerometers, gyroscopes, and compasses, sensor fusion techniques can enhance position estimation and compensate for GPS signal limitations. This approach is commonly used in smartphones and wearable devices. Overall, while GPS is primarily designed for outdoor use, advancements in technology and complementary positioning methods have improved indoor positioning capabilities. However, the effectiveness of GPS reception indoors or in obstructed areas still depends on the specific environment and available infrastructure. Indoor positioning systems, IPS, have gained popularity and are being utilized in various applications to provide location-based services and navigation within indoor environments where GPS signals may be limited or unavailable. Here are some common applications of IPS. 1. Indoor navigation and wayfinding. IPS enables users to navigate and find their way within complex indoor spaces such as airports, shopping malls, hospitals, museums, and large office buildings. IPS can guide users to specific points of interest, provide turn-by-turn directions, and help them locate amenities, exits, or specific rooms. 2. Retail and indoor marketing. IPS can be used in retail environments to enhance the shopping experience. Retailers can offer personalized promotions, product recommendations, and targeted advertisements to customers based on their location within the store. IPS can also help retailers analyze customer traffic patterns and optimize store layouts. 3. Asset and inventory tracking. IPS can track the movement and location of assets, equipment, and inventory within indoor facilities. This is particularly useful in warehouses, manufacturing plants, hospitals, and large-scale retail stores. IPS can improve inventory management, reduce theft or loss, and optimize resource allocation. Indoor analytics and heat mapping. IPS can collect data on foot traffic, visitor behavior, and movement patterns within indoor spaces. This data can be analyzed to gain insights into customer preferences, optimize space utilization, and make informed decisions regarding operations, staffing, and facility management. Indoor safety and security. IPS can play a role in enhancing safety and security within indoor environments. It can assist in emergency response by guiding people to exits or safe zones during evacuations. IPS can also be integrated with surveillance systems to track and monitor the movement of individuals in sensitive areas. Healthcare and asset tracking. IPS can be utilized in healthcare settings to track medical equipment, monitor patient movement, and improve workflow efficiency. It can help locate specific medical devices, manage bed availability, and streamline patient flow within hospitals or clinics. Museums and exhibitions. IPS can enhance the visitor experience in museums and exhibitions by providing interactive and location-based information about exhibits, artwork, or artifacts. Visitors can receive detailed descriptions, multimedia content, and contextual information based on their precise location within the facility. These are just a few examples of how IPS is being applied in various industries. The specific applications and features of IPS can vary depending on the system implementation, infrastructure, and requirements of the indoor environment.